Welcome. My name is Godswill Nwankpa. So this is a chemistry topic. This is about Beer-Lambert's law in practice. So I'll describe what Beer-Lambert's law is first. So A here is the absorbance, and this E-like figure is the molar absorptivity, and that means that's the substance and that's the substance like intrinsic property that shows like how strongly that substance absorbs light at a specific wavelength. And then L, also sometimes denoted as P, is the path length, or in other words, the length or like the width of the cuvette. Like from right here to like right here, which is usually a 1 centimeter in like labs. And C here is the concentration. The concentration is simply the amount of solutes in a given volume. So like how densely packed or like lightly packed it is. So let me show you where our demonstration or experiment would be. Welcome to spectrophotometry simulation, Beer's law. So the purpose of this experiment is to see how Beer-Lambert's law in practice, which relates the direct linear relationship between light absorbance of a substance and its concentration. The ultimate goal of this experiment is to demonstrate how light absorption can be used to calculate the concentration of a substance, and in fact, any substance for that matter. Now, briefly, here's the idea of what will happen in this experiment. Using this blue stock solution, I will create a series of increasing dilutions of the stock solution here in each succeeding tube, with the last of the tube. This one that says blank. As you go from left to right, will be water in our case. That's going to be just the solvent only. And each of these two dilutions will be transferred to a cuvette, which will be placed in this standard lab colorimeter that will then measure the absorbance or transmittance of the solutions, or in other words, how much light passes through the solutions at a preset specific wavelength, like the 630 nanometers that you see here. And as we collect our absorbance values, an automatically generated calibration curve here will be created for us. As we get our absorbance, it will calculate the concentration for us automatically and create a calibration curve, or basically a graph. And this calibration curve or graph is made by plotting the solution's absorbances and their known concentrations. And now, if you are wondering how the concentrations of the sample were found, since we were not originally given them, as you will see later in the experiment, well, nice catch. You see, after finding the relative absorbances of these samples, after we have put them in the colorimeter, all one has to do is to plug it into Beer-Lambert's law, and we then rearrange the equation to find the sample's concentration here. Because the molar absorptivity is like constant. We would already know that we should have been given the molar absorptivity of that substance, and the path length is usually 1 centimeter, and the absorbance will be what we get from the colorimeter. So just rearrange the equation and you find the concentration. Then you can make that graph. And so after creating this calibration curve, we can now use that curve to find the concentration of an unknown sample. It's gonna go maybe something like this, for example. And then now I want to this are our unknown drink that's over here, our unknown sample. Once we then measure its absorbance value, using our calibration curve, we can just look at where its absorbance lies, and then trace a line here, see where it lies on our like linear graph, and then plot it, like go down, search for its absorbance, and then you find maybe it's like 1.90 something. So yeah, now let's begin our experiment. I'll show you the demonstration. So first, it says prepare a sample, the stock solution. Fill fill the first tube with a complete stock solution. 10 milliliters, and then fill sample 2 with 8, and then fill sample 2, or just call it like tubes. Fill tube 2 with 2 milliliters of water. We're diluting solutions that we're making. So now fill this one with 6 milliliters, and now 4 milliliters of water. We're trying to get like a range of samples with different concentrations or absorbances, so that we can be able to create a line. So it wouldn't make sense to just create samples with only the same absorbance or concentration. So that's why we're making a range of diluted solutions. So now I'll fill to 4 with 4 milliliters of stock solution, and now with 6 milliliters of water, our solvent. So you'll be watching the directions there. Now I fill it with 8 milliliters of water. Now we filled our last tube with just the solvent, like I told you guys. So now I have to make the spectrophotometer. This device is called colorimeter. This is like a broader name. So I have to make this 0. Hold on, wait. Yeah. Oh, sorry. Fill pipettes. I've done this many times, but quite sick right now. It's affecting my seeing ability. So take some solution, some solvent from that, and place the cuvette in the spectrophotometer. And I'll click the 0 button to like reset it. We don't want it to take a measurement of our for our solvent only. Okay, so because that's 100 transmittance or absorbance, 0 absorbance of light. So now drag that to waste. So now we need to fill the pipettes with some water. We need to rinse it. We don't want it to be contaminated. We don't want to like contaminate the next solution that we're gonna drop in. Because now we're gonna take some of tubes 2 solution and place it here to measure its own absorbances. Oof. Haha, you didn't see anything. Okay, so measure. There. Now fill the pipette with water. You see why we need to rinse it? We can't have the water mixing with the next solution that can't have the water mixing with the next solution that we're gonna put in. Need it to be the exact representation of what we're putting in. It should not be diluted by the water. Oof. Quite sick. Alright. Keep that in the waste. We need to rinse it now with some water. Put that in the waste. Take the degrees solution. Measure that. You see, as we're getting this, it's plotting our graph there. Try to get a sense of what this means. It's just showing our results. Okay, so yeah, I measured that. Now put it in the waste. Oh, sorry. Need to be extra careful as a scientist. You see, although I'm a renowned scientist, I'm making so much mistakes. So imagine you guys are still not at my level yet. So imagine how much more mistakes you'll be making. See, this goes to show how serious this is. You need to have complete concentration. But I try to focus on what we're doing. So I have to rinse this. You know why we need to rinse it? Okay. So now let's. Oh, sorry. Yeah. Haha. So now I measure it to 5, 0.06 absorbance. Where is that? No, sorry. Here it is. 87.1% transmittance of light. That's how much light passes through. So now put that in the waste bin. Now we can measure our. Oh, sorry. After we rinse it. So yeah, we rinsed it. Now we put 3 milliliters of the solvent into our cuvette. Now we put it into our colorimeter, measure. As you can expect, it's 100% transmittance of light. Now we fill our pipettes with water. We're rinsing our cuvette, making sure it's free of any of the other particles of the solutions. Now we can measure the concentration of this drink because we don't know what it was before, and there's no way we could find it without this. So now let's see. Try and guess where that would, lie on this calibration graph or curve that's already created for us here. It looks to be kind of the same, like darkness, I would say. Maybe it would lie somewhere here, or maybe a little further. Measure. 39% of light passed through. Okay, let's see. Oh, this was like way ahead. Yeah, as you can see, that's how it works. By making our calibration curve, all we have to do is find the absorbance of this unknown sample and then plug it into an equation that was supposed to be here. Because since you can make a graph, you need an equation to make that graph to plot it. So yeah, you just plug that absorbance into the equation, and then you can find your concentration. See, that's where it is. Yeah, thank you.